Physical reality of electromagnetism relies on three specific vectors: magnetic field, current, and physical force. In three-dimensional space, they always operate at strict 90-degree angles to each other. Instead of trying to memorize the hands first, start with a diagnostic approach. Ask yourself, what are you trying to find? Your starting variables dictate exactly which rule to use. You will face one of three paths: finding a magnetic field, finding a physical force, or finding an induced current. Accuracy in these problems depends on correctly diagnosing the physical scenario before choosing a hand rule. Let's start with the first scenario. You have a straight wire, you know the direction the current is flowing, and you need to find the direction of the magnetic field it creates. Take a look at this diagram detailing Maxwell's right-hand grip rule. Pointing your thumb in the direction of the current is your first known variable. The natural curl of your fingers reveals the circular direction of the resulting magnetic field lines. When you are dealing with negative electron flow, you must mirror the process using your left hand to find the correct field direction. The grip rule has a hard limit. It only maps the field. If you place that current-carrying wire into an external magnetic field to generate physical movement, the grip rule becomes useless. This illustration shows a classic motor scenario, where you have an existing magnetic field and a power source driving a current through a wire. This diagram outlines Fleming's left-hand rule, the tool for calculating force and motion in electric motors. We use the FBI mnemonic. The forefinger represents the magnetic field, the center finger points along the current, and the thumb reveals the resulting force. This rule is incredibly fast for exam recall, but it remains prone to error if you forget it applies exclusively to motors, where electricity creates motion. Reserve your left hand specifically for problems where electricity is being consumed to produce movement. Now for the third scenario. You have a magnetic field, you are physically forcing a wire through it, and you need to find the direction of the induced electrical current. This relies on the principles of electromagnetic induction, discovered by Michael Faraday. This is the basic operating mechanic of a generator. For this, you switch to Fleming's right-hand rule. The physical shape of your hand remains identical to the motor rule. The risk of error here is high because your inputs and outputs swap places. Your thumb is now the known input, the physical motion, and your center finger gives you the unknown output, the induced current. Look at this slide outlining the Lorentz force law. It offers an alternative for the conceptual optimizer. Force equals charge times helmicity cross magnetic field. By using the right-hand vector cross product, often called the palm rule, you sweep your fingers from the velocity vector to the magnetic field, and your thumb points to the force. One hand can solve every force problem. While Lorentz eliminates the risk of swapping your left and right hands, it introduces the negative charge trap. Conventional physics models treat electrical flow as a positive charge, but the actual electrons physically moving through the wire are negative. That negative charge acts as a mathematical flip, forcing a strict 180-degree reversal of your predicted force vector. If you choose the Lorentz method, you must either reverse your final answer for electrons or perform the cross product with your left hand to correct the math automatically.